Hello, so I'll be actually probably I'll go through some parts very fast and spend more time on some details. So I have quite a few aspects. So I'll go fast on the general presentation, just reminding us that EDF has quite a few reasons to work on many computer simulation tools for different aspects of what our priorities and needs are. And as one of the largest nuclear energy producers, we have quite a few aspects that can relate to what we do in the department I work in. And for many of these reasons, there's been quite a bit of code development at EDF R&D for many years, actually. So there are codes in CFD, code Saturn, which I'm going to be talking about. A two-phase, multi-phase model actually which works with that, but there's also a large structural mechanics codes, free surface fluid codes, many other more specialized codes, integration platforms such as Salome, open terms for VVUQ, and many others which I'm not mentioning. So this is just to say that there is quite a bit of development activity or use of existing codes and collaborations in many aspects. For example, in a nuclear power plant, there are many places where we can need a CFD or where it can be useful, whether it's to check safety aspects, such as what happens if you have a fire someplace and make sure it doesn't do too much damage. Some other incident or accident simulations, checking that the fuel pools remain in the correct temperatures, improving the performance of the heatsink for the overall power output, other maintenance aspects of the environment on the plant, aspects of the plant on the environment, etc. So that leads not only to many fields which can require CFD, but also many different models and different types of studies that we can be led to do. So we've been developing Code Saturn over the last 20 years, and there were codes at EDF before that. So it was based on the prior experience also. And so the code has been open source for quite a while for different reasons of transparency, making partnerships easier. And it has pretty classical quality assurance since it is used not only in, but in part in nuclear studies. The quality assurance aspects are very important. So I'll just go fast on that part, and just to highlight a few of the multiphysics models we can have mesh deformation of ALE. We have some modeling for electric arcs. We can add a Lagrangian particle tracking model on top of the Eulerian model. There are some specialized models for atmospheric flows, some specialized models for fire modeling, classical thermohydraulics for nuclear applications, and other ventilation, for example, applications will use quite advanced turbulence models in quite a few cases. A lot of different and advanced RATS models, LES. It can go up to the DNS, though it's not specialized for DNS. And some other combustion models, which are not used as much. Groundwater flows, which is not really Navier-Stokes, which is simpler flows, but which can be used with the same tools. Some turbomachinery aspects, etc. And a few industrial examples, for example, are some turbulent flow through a pressurized water reactor guide card, where we observed that some control rod vibration with large displacements could also lead to premature wear of some components, which means you had to change them and refit them more often than necessary, or at least than initially planned. And for this type of a calculation, we needed a pretty large wall-resolved LES on one plate, and that could lead to a 1 billion cell mesh. So this is one of the larger studies. We have plenty of other smaller study examples. Since we're talking about exascale here, this is a good example of what we can do on, let's say, at the high range of industrial studies. And the mesh was just generated in part with an external mesher, and then extended with in situ aspects. I'll detail more a bit on that. And well, here's a short extract of what this code provides. So pretty detailed LES, and same thing with some extracts. Other examples: fictitious fires in reactors, just to see what can be damaged, how the fire can be stopped early. And so these are more shorter computations. And the code needs to handle both. And the more recent application is groundwater flows, where we try to check how flows could seep and how, which can be related to different storage aspects, using different models. And so in this case, here is another computation that was also on large meshes, generated out of many parts for such models. So I'll be moving to the HPC aspects of Code Saturn. And basically, well, Code Saturn and its Neptune CFD 2 multi-phase extension have been used extensively on quite a few HPC machines. So on our own clusters, on quite a few Prace machines we've had access to, either directly or indirectly, DOE machines, including Jaguar, Summit, Vera, and so we've had quite a bit of collaboration, especially with STFC Daresbury, and also with IMFT, but a lot of work with STFC over the several last years to go to the high, large meshing sizes. A lot of work mainly on the checking, debugging, and debugging at scale of the code. So basically, that's in that sort of collaboration that we first were able to reach 1 billion cells, and now 1 billion cell might not be routine for the average user, but if you do need that size mesh, there's no reason you shouldn't be able to run it, assuming you have a powerful enough and stable enough cluster. And so production runs above a billion cells are now relatively routine. And so it's one of the 12 codes selected for Prace and DESA UABS benchmark. So how does the tool chain work? It's a reduced number of tools. You try to keep things simple from a user point of view. So it's managed by a common Python script. And basically, we have a graphical interface which just basically only generates input files and gets out of the way. A preprocessor which basically imports meshes. And everything else is now in the main solve, including some pre and post processing aspects. So this gives us a good separation between the interactive and the long-running parts. And the long-running part is the part which is parallel, works with MPI, etc. So this is where I get to the parallelism aspects. Nothing extraordinary or original here. Basically, mainly based on MPI, partition data, classical model, and mainly bulk synchronous parallel model. And then we can have secondary levels of parallelism. So shared memory based on OpenMP, which is actually some work mainly done a few years ago, which is mainly loop-based. So it's definitely not as good as MPI, even on a single node for most operators. Some operators are not OpenMP enabled, so only the major one or highest intensity ones are. But it does have less overhead and memory usage than MPI, and when we do mix the two, we can scale a bit further, at least at the end where we start having MPI issues. And we can now we started working for GPUs, and now, for example, we can use the AMGX library for linear solvers, which is a recent addition to the code. So another type of hybrid parallelism. So for the MPI part, we use classical domain mesh partitioning, and we can either use graph partitioning libraries like Parmetis or PtScotch, or internal space filling curves algorithm like Morton or Hilbert's curve. And the space filling curve was added quite a few years ago, and we were definitely happy we added them, because on large cases, we often have robustness issues with Parmetis and PtScotch, while the space filling curve is deterministic and basically always works. So the performance is usually slightly lower, but at least it's a stable and workable solution. And then we just use classical ghost cells with some specificities in the way the ghost cells are numbered, but the approach is classical. And the periodicity is also a true geometric periodicity based on ghost cells and not on boundary conditions. And we have quite a few parallel and pre and post-processing features. So basically, we can do a lot of modification of the mesh in parallel, and that allows us to work around several meshing tool limitations. One of the big limitations is just that not many meshing tools are parallel. It was mentioned in the previous slide. So we can join meshes on arbitrary interfaces, whether they're conforming or not. And basically, we can read a mesh by pieces and assemble them online in the computation and join everything. So that has basically mitigated the limitations of meshing tools for quite a few years. And then we can also more recently extrude boundary faces, insert boundary layers, have a mesh refinement engine that's been added pretty recently, and which has been tested up to several over 100 billion cells, actually 512 just for the pre-processing this year or last year. And we also have possibility of defining extracts using arbitrary combination of post-processing writers and meshes. So in situ extracts, and possibility of linking with in situ dedicated libraries like ParaView Catalyst or Melissa for ensemble runs. And so I'll go pretty fast for the parallel mesh joining, but just to say we do need quite a bit of data movement in those parts. Make sure all processes agree and take the same decisions. But basically, we're able to handle that pretty well without changing algorithm too much, and while improving some underlying location libraries pretty recently. For in situ post-processing, we use Catalyst. So basically, for those who are not familiar with it, it's a subset of ParaView based on VTK, and it can allow running basically off-screen rendering. And the main concepts are just that you need an adapter from the code to the VTK library, and then it handles its pipeline. So it's quite simple to set up for a user the way we plugged it. It's a pain to install, but once it's working, it's very nice for users. It allows us limiting I/O, making post-processing possible at high ranges. We also have direct extracts in the code where the user can select based on different criteria, including variable-based criteria, which portion of the mesh is extracted, and also reduce data this way. A few numerical features of note to HPC for CodeSetter is that it's a segregated solver, so all variables are solved independently. Coupling terms are explicit. And we have some terms which have matrices with dense diagonal blocks and sparser off diagonal blocks. So we do use specific matrix storage variants, which are basically variants of MSR, which can reduce the bandwidth by a factor of almost 10. And we solve with increments, which means we have a lot of multiple sweeps and sub-solves. So none of this is good for HPC because it leads us in our BSP model to have a lot of synchronization and quite a few all reduces, so implicit barriers all over the place. But it's what we've been working with, and on newer approaches, we have new discretizations I'll be talking a bit about, in which we try to get around this and move to more coupled aspects. And basically, in the legacy variant of the code, linear equation solvers can go from 90 to 40% of the compute cost, and gradient construction, which is more specific to our discretization, is about 20 to 60%. So one part can be handled by external libraries, and other parts cannot. And we have a basically memory-bound code. For the evolution aspects, which is in the title of the presentation, this is a mixed C-Fortran code. The code started in 1998, and people at the time were mainly physicists and numericists, and most of them did not have a computer science background, didn't want to hear about anything else than Fortran 77. And then we obviously needed to go beyond that. And we've been improving the code and migrating towards more C-based things. Modern Fortran would have been nice, but basically it came too late. And one of the nicer aspects is we only have compiled code, so we avoid debugging nightmares, though maybe I think some very recent versions of Total you might be able to handle mixed Python and compiled code, but that's so we might not have rapid development languages, but then we avoid other issues around that. And we have a bit of C++ for other adapter codes. It would have been nice actually using C++ earlier, but old timers didn't want it, and some people pushing it were not helping by not being very rational about it either. So, and side effects was short names which require renaming a lot. So there is basically just to say that there's a lot of ongoing work that's been basically done over the years, and that continues with a lot of refactoring work, which is necessary to keep the code in shape. And one of the things I'll be a bit faster in this part, but for example, we have to keep things simple for the users, we can switch between the partitioning numbering and some flat block-based numbering where we have elements in the initial unpartitioned order. This allows us to do some matching of elements in a simpler manner, to have I/O on files which are independent of the partitioning. So this is used quite a bit. We don't use it in the middle of a solution, but it is used in quite a few places. And this does lead to data movement, as the example here shows. Have the same thing when we're sharing elements when we have elements that are shared across processors. In the first example, I was showing cell numbers, which are only on one processor. When we have shared elements, this can be used for matching those. So this does require data movement, but using this sort of thing, we've been able to have very stable algorithms, simple to verify, which have been robust for all the ghost cell generation and such. So this does, we have refactored that over the years to make it simpler to use, and refactoring it has had an added benefit, is to allow instrumentation in an easier manner. So a lot of built-in instrumentation in the code, a lot of local timers. So I'll skip on that. But basically, this instrumentation has allowed us to check where we have memory peaks when we're running the code. Also use simple tools like valgrind on a single rank. And same here with a node setting of the code, we could see where we had a memory peak using one algorithm. Switching in another algorithm made possible with the API, we still had the same issue, probably worse. And basically seeing exactly where that happened has allowed us to improve that. So basically just instrumentation, classical work, but a lot of built-in things in the tool, which we've added over the years to improve it. And we see the communication statistics can help us see also what type of heterogeneity we have in a single operator, and that can help us in the future to build heuristics and specialize that in a more easy manner. So I'll go quick on those. And the experience on this has also allowed us to have more specialized algorithm. For example, when we're assembling matrices,
apologies, 5 minutes left.
We can use range sets, which will allow us to use classical assemblies like hyperinfancy. So I'll go faster on this. A lot of work has been on new discretization schemes. So there's work in progress here, which are done so that designed to be more robust on polyhedral distorted meshes with a lot of upstream verification. So I'll just go fast on that. And since this is newer code, well, it was written with modern architectures in mind, and basically we have much better shared memory behavior. Cellwise approach, which is more cache friendly, and especially better interoperability with external libraries. just an example of the groundwater flow module with that, and the scaling where we, in this case, we can make pretty good use of threading. So I'll go fast on those aspects, just to show that in recent developments we've been able to integrate better with external libraries and leverage that for linear solvers. And then finally to move to hybrid parallelism. So I only have a few minutes left. We've had OpenMP, as I mentioned, working since a few years ago. OpenMP loops is still very painful to use. Thread races are really a pain to debug, especially for lack of tools or of good tools. And writing the code in C instead of Fortran, for example, makes local or private loops easier to build and allows avoiding a lot of those bugs, but it still is quite painful. And the advantages are not so huge in most cases. But it is basically a safety for the code for cases where MPI reaches its limits. We've also started working a bit on GPUs. So before we plugged the MGX, we've also had some experiments on our own solvers. And basically this allows us to see the range where the CPU is happier and where the GPU is happier. So I'll go fast on that. It's pretty classical. We need more data and larger data sets on the GPU to keep it busy. And latencies are smaller on CPUs, obviously, so nothing very original here. And work on also with IBM and STFC on developing, adapting some of our algorithm to GPU with interesting results. And basically, other future directions, we're going to continue leveraging external libraries where relevant, push to more in-memory data staging to avoid files probably with conduit for the evolution or ParaView, maybe test ADOs or HDF5 or some such things, or HDF5 variants to mitigate IO volumes. Try to be yet more careful with auto operations and keep up with, say, in situ libraries. Catalyst is fast-moving target, but it still is interesting, and better adapt to heterogeneous resources. So we have a push for GPUs and try to adapt the code. We can afford to do a bit of vendor-specific coding for a few kernels, which will need to use directives or maybe new language features for the rest. And so we're starting on that now. Libraries are easier to plug for the built-in parts. We'll be working on that, and that will require further factorization. We also have a PhD starting to experiment with machine learning to assist for some aspects performance tuning. And that's it. So the code will continue to evolve. It's under an open source license. We're happy to collaborate with anybody who's interested. And that's it for my presentation. Thanks for your attention.